Okay, so today we are going to continue in this chapter and we will cover the remaining topics. We have started electromagnetic waves, and electromagnetic waves is a small chapter. Maximum 4 5 classes it can be open, but of course we are solving more problems, so it may take little more time, but that's okay. Okay, we'll finish everything in this chapter. Okay, so let's start uh, remaining topics. So we have covered about the background of this chapter. We have covered about displacement current. We have seen inside the capacitor how the electric field is changing and how can we calculate magnetic field inside the capacitor. Okay, that means using the displacement current. Okay, and few problems we have seen, NCERT questions we have seen, and we have seen other problems also. Then today we will move into the next topic, that is the Maxwell's four equations. Maxwell's equations of electromagnetic waves. Maxwell's Maxwell's equations of electromagnetic wave. There are two equations which are similar and two other equations which are also similar. So total there are four equations in this, but those four equations which are given in NCERT in most of the textbook, that you have to remember, definitely you have to remember. Beside this, I will give some other version of this which are present in many other highly standard textbooks. May not be in NCERT, but in other textbooks they may be present. Those version also I will discuss with proper meaning. Okay, so let us see first two equations. First two equations are related with Gauss law in electrostatics or electricity, and Gauss law in magnetism. So all of you know about Gauss law. Gauss law, if you apply electric field dA, E dot dA, this is nothing but electric flux in a closed surface is equal to charge inside by epsilon naught. This is Gauss law, Gauss law in electricity or electrostatics. Then B dot dA, magnetic flux in a closed surface. Similarly, magnetic charge, but magnetic charge monopole do not exist, so this is going to be zero, that we know. This is Gauss law in magnetism. Gauss law in magnetism. Then the third one is Maxwell has modified Ampere circuital law, so he has given that law. All these law, some of this law he has not given, but why are we writing his law? All this because he have used all this to combine electricity and magnetism, and he has given the concept of electromagnetic waves. And in deriving the electromagnetic waves, which you will be studying if you are going engineering, then you will be studying that in the special courses, like if you are taking some courses on light or electromagnetic waves, you will be studying that. Okay. Yes. Yes. That is why Maxwell has utilized it further, these equations, to derive the theory of electromagnetism. The theory of electromagnetism or electromagnetic wave is not in your syllabus. Yeah, that is a very vast theory in research. Okay, Maxwell, not just Maxwell has given this, Maxwell has used this to derive or to combine the concept of electricity and magnetism. So Maxwell says that the electricity and magnetism, they are not two independent things. They are mutually dependent on each other. In fact, electricity and magnetism are same thing, right? But they are like totally interrelated. They are not two different things. So he has given the theory of electromagnetic waves, which you will be studying in higher grades if you are going engineering. So right now in this chapter, we are not studying much about electromagnetic wave theory given by Maxwell, right? That is not in part of our syllabus. Okay. So in order to derive those theory, he uses these equations, right? So he uses all these equations. That is why we call them as Maxwell's equations of electromagnetic wave. We are not simply saying Maxwell equation. Maxwell equations of electromagnetic wave, because the electromagnetic wave theory which was given by Maxwell, that theory was using these equations. Okay, that is why it is called. Right. So this is Gauss line magnetism. Then another thing is that line integral of B dot dl, or first let us take E dot dl. Line integral of electric field E dot dl is equal to, this is like EMF, hmm, EMF, that minus rate of change of magnetic flux d phi b by dt. This is actually Faraday's law of electromagnetic induction. Faraday's law of electromagnetic induction, EMI. Okay. The fourth one is similar to this, that is the Ampere's orbital law. Integral of B dot dl over a closed path is mu naught into current inside, which current inside is written as IC plus ID. ID is written as epsilon naught d phi e by dt. This is Maxwell Ampere law, or Maxwell Ampere orbital law. Okay. So all these four laws, they will ask in your in NEET, if they are asking in NEET, they will ask, they will give some four equations and they will ask which of them is Maxwell's equation of electromagnetic wave, or which of them is not a equation, Maxwell's equation of electromagnetic wave. So we must remember the first two equations are related to surface integral. Okay, this is surface integral, this is also surface integral, but the surface integral of electric field, it is surface integral of electric field, electric field over a closed surface, over a closed surface. And this one is surface integral of magnetic field, surface integral of magnetic field, magnetic field over a closed surface. So first two are surface integral, next two are line integral. This is line integral of electric field over a closed loop, closed loop. Similarly, this one is line integral of magnetic field, line integral of magnetic field over a closed loop, over a closed loop. Okay. Now I am going to give a different version of this which may not be present in the textbook. Okay, so one by one I will write it and I will also explain that. So this is the normal equations which are given in textbooks. Okay, if you want to note it. Yes. Yes, 11th session also night we will have. Timing we can start around 9 or 9:30. Any 11th students also, if you know, you can tell them to join. Okay, so let us see the another version of this. Another versions one by one we will see because you may not understand everything if I write. So let us first write this. Uh, this first was Gauss law. Now Gauss law in electros. First Gauss law I will write. Del vector dot rho, sorry, del vector dot d vector is equal to rho. Now you will say that I have never seen this equation, but this is what is Gauss law in electrostatics or electricity. This is Gauss law in electricity, right? So how this is correct? You may ask how that is correct, right? So let me explain this one by one. I will do that. Okay. Del vector, meaning of del vector, I hope you should know. This is dou by dou x I cap partial differentiation dou by dou y j cap plus dou by dou z k cap. Okay, and displacement vector is a vector which is epsilon naught e vector. Okay, so let us and what is this then rho? Rho is charge density, volume charge density. Yeah. Volume charge density means charge by volume. Okay, I will explain how this is satisfying, how this is the Gauss law in three dimension. Okay, I will explain that. Suppose I take only one dimension. hmm, One dimension, that means I take only one D. So dot product means what? This is dot product means what? Dou by dou x I will take dou by dou x. Okay, epsilon naught of electric field along x-axis it will be. Okay, let us say that's the only electric field. So this will be left hand side. Right hand side is charge by volume. Volume can be written as dx dy dz, dx dy dz. Okay, small charge by volume. Now this I will multiply. So dx, dy, dz get multiplied, and this partial differentiation can also be written as single differentiation. Now you write it as a single differentiation, d by dx. Okay. So d epsilon naught e by dx, dy, dz is equal to charge. This epsilon naught can come out of differentiation, and here dx, sorry, here in the numerator we have only d, right? Numerator we have only this d of this, and here dx is only there in the numerator. So denominator we have only dx, right? This I am cross multiplying. This time I am cross multiplying. This become dx, dy, dz, right? So what happens now is this dx get cancelled. So we are left with uh, epsilon naught can be taken out, and this d of e will remain, and this is dy dz will remain, and this will be charged. This epsilon naught I will take that side. So charged by epsilon naught, and this is like electric field and a small area. That electric field you can take as constant, and this is like a small area. That's what when you integrate this, when you integrate this left hand side, that becomes EDA, right? This also can be written as a small charge, okay? dq you can write. So when I integrate, that integration of dq will be charged by epsilon naught. This is what is Gauss law now. Yes, can you see? This is Gauss law. Integral of surface integral of electric field. Circular means closed surface. Charge inside by epsilon. This version is not present in standard textbook because this idea requires once in J I have proved it, okay, but that also in a problem I proved it. Okay. So here, because in order to introduce these terms, you need to know this term. Unless this you know, charge by volume. This also somewhere you have studied in grade 11. Okay, this D factor is not studied. This is called displacement field. Displacement field. Displacement field vector. Displacement field. Yes. Okay. Earlier 6 o'clock. Yeah, we'll try that. Whenever I don't have this, because study hours are also there na, some other days. Oh, oh, you are only asking for today. Today you are asking. Uh, why evening you are going somewhere out? Okay, we'll try. I will update you. Possibility is there, so I will update you. If you can have it. Right. It's okay. Huh? Okay, so now also note that this form that we are writing, uh, this is called differential form. I will write each equation in different form. One is called differential form. Differential form. Now let us write the same equation in integral form. Integral form is like that integration. But this time when we are writing integral form, we will write like two integral we will write, and we'll put one big circle. Okay, this symbol you might not have seen. D factor dot area vector dA vector is equal to, this side become triple integral rho into dV. Okay. This is over a area or surface, over a surface. This is over volume. So this form is also the same Gauss law in electricity, but this is in integral form. Integral form. Here closed circle means over a closed surface we are taking. Double integration means, because area, whenever integration is over area, it is called double integration. Triple integration means whenever integration is over a volume, that is called triple integration. But here, this triple integration circle is not there, that we note. Some volume is there. Okay, so similarly, the second law also we will write, Gauss law in in magnetism, the second equation, that we will write del vector dot V vector. That is going to be 0. Okay. This is Gauss law in magnetism. Again, same thing, you know about this. Del vector is what you know that. This is this is differential form. This is differential form. What is integral form of this? Integral form is again like this. 2 integral circle d dot dA is equal to 0. This is over surface. This is integral form. Okay. So two equations are over. Let us move to the next equation number 3 and equation number 4. 3 also will have differential and integral form. Equation number 4 also differential and integral form. Okay. Del cross E vector is equal to minus dou B by dou T, partial integration. This equation is differential form. Differential form. Which equation, which law it is? It is Faraday's law of electromagnetic waves. Okay. And its integral form is integral of E dot dl is equal to minus surface integral of surface dou B vector dou T dot dA vector. This equation is integral form. Okay, then last equation number 4, del cross H vector is equal to J vector plus dou D vector by dou T. This is Maxwell Ampere law. Okay, differential form. Order of equations are same only. Differential form. And integral form is H vector dot dl is equal to double integral over surface j vector plus dou d vector by dou t dot dE vector. This equation is integral form. Here a new term is coming which is H vector. H vector you have studied in magnetism. Tell me what is H vector, and J vector you have studied in current electricity. You remember? J vector is current density. Current density is current by area. So vector quantity. H vector is magnetizing field. Magnetizing field, which is nothing but n into I, but it is a vector. Or it is B vector by this H is same. This H vector is same. Remember this H vector? This H vector, B is mu H, right? B is mu H. So this is B vector by mu. That's the same, right? And J is current by area, but it's a vector that we know already. B vector by mu. Okay, so with this we are finding these four equations. Then we will move to the next one. All of you have noted this? Yes. Anyone any doubt in this? You need to remember these four version also which are integral and differential form, because in tough question if they ask, if they want tough question, then they will give in this form, then you will not be able to recognize it. These are Maxwell's equation only. Okay. Fine, so let us move then next. We are going to move next, which is nothing but the source of electromagnetic wave. Source of EM. Source of EMW is oscillating charges. Oscillating charges. So if the charges are oscillating, it will produce oscillating electric field or oscillating magnetic field. Let's try to understand this. Suppose this is a charge plus, this is charge minus. Let us say that this is the mean position of this charge. This also it is the mean position of this charge. Now I will give two example of oscillating charges or oscillating electric field or magnetic field. Okay. One is the charge itself is moving. The charge itself is moving. That moving charge is moving just like a simple harmonic motion. They are moving. So suppose this charge is here and this charge is here. So you know the electric field goes from positive to negative. This is electric field. And you can draw various other electric field lines. This type of lines we have studied in electric dipole, right? Right, this is electric field. Now suppose if this charge is moving, let us say it goes to extreme position. So suppose this charge comes, this positive charge comes little bit this side, and this negative charge also moves this side. Then what happens? This electric field lines also will be there. So now it will be going from here to here. Same way it will go. Okay, I am drawing the next set of electric field lines like this, like this, right? So as it is going away, let us focus on only one electric field. Let us focus this straight line electric field which is joining these charges. Let us focus on this electric field line. As they are moving away, this electric field line, this value is going to become smaller. Anywhere in between you can study that. I'm not saying you have to study everywhere. Let us fix a point in between. Okay, let us fix a point somewhere exactly in between the charges here. Let us focus at a point. Here you focus. So suppose the charges, if let us say here, now the field is larger, but if the charge distance increases, this field value will decrease here. The value will decrease. Okay. So as the charges are oscillating like this way, when they are coming closest, the field is strongest, and when they move farthest, the field becomes weakest. So there is a maximum value of field and there is a minimum value of field. So electric field at any given point in the space surrounding these two oscillating charges, at any given point, electric field is becoming sometime maximum, sometime minimum, sometime maximum, sometime minimum, and some other times it is in between them, right? So electric field at any point in the space is changing, it is becoming maximum, minimum, maximum, minimum, maximum, minimum, like that, and of course in between them. So that means if they are oscillating, then electric field is also oscillating. So you can say that oscillating charges produces oscillating electric field, produces oscillating electric field, electric field. Now, as soon as this oscillating electric field is produced, it will produce a changing magnetic, because this oscillating electric field means electric field is changing, right? So there is a maximum and there is a minimum. So I can write this electric field at some amplitude E naught, let us say sine omega t. This type of equation represent electric field varying sinusoidal, right? This type of equation represent at a given point how electric field is varying sinusoidally, like this. So there is a maximum electric field E naught plus E naught, and there is a minimum electric field minus E naught. And at other times it varies in between maximum minimum. So electric field oscillating means electric field is not a particle which can oscillate like a block or a mass, right? Like a spring mass system you have studied. So electric field is not like that, but oscillating electric field means electric field value changes in a sinusoidal manner. That's a changing electric field. Okay, but when we say charge oscillating means definitely charges are moving, or you may also say the value of charge is oscillating. That also you can say that physically the charge may move. Charge is the same charge, but physically the charge may move, or charge can vary like sinusoidally also. That is also same. Charge can also vary. Do not sine omega t. This is also like a oscillating charge. This is also oscillating charge. Oscillating charge. So oscillating charge can means charge value changing, or physically charges are oscillating. Oscillating charge may include physical motion, physical motion of charge particles. So if charge particle is physically moving, like this diagram which I have shown here, this I have shown physical motion of the charge, like just like a simple harmonic motion or spring mass system, charges are moving. Same way I have shown here, Charges, opposite charges, equal and opposite charges are moving, right? It's like an electric dipole, you can say. It's like electric dipole. Okay, electric dipole is moving, sometimes coming close, far, like that it is happening. That type of oscillation of charge will produce oscillating electric field, and this oscillating electric field will also produce magnetic field, but in perpendicular direction. Perpendicular direction means what? Perpendicular direction means this circle is in plane of this, right? It will produce like this kind of magnetic field, like this. So these lines which I have shown, these are magnetic field lines, magnetic field lines. Okay, so these magnetic field lines will be produced because suppose current is like this way, you know that, right? If current is like this way, so magnetic field is around this. It's like in the capacitor problem we have seen, right? Electric field was like this, magnetic field is like this way, perpendicular to this plane. It's like there is a wire carrying current, so electric field is along this direction, magnetic field is along this direction, right? That we know. The diagram will look definitely complex. Okay. So magnetic field oscillate means what? Magnetic field also will vary sinusoidally only. Magnetic field also will vary like that, B naught sine omega t. Like this only it will vary. Okay. Like this it will vary. So that means the changing electric field produces changing magnetic field. Changing means oscillating. Oscillating means simple harmonic function it will be. How changing electric field is produced? Changing electric field will be produced by how? By either charges are moving or charges may be changing in capacitor plate. Like this type of formula you must have seen somewhere. Where have you seen this? Have you seen in LC oscillation circuit? Have you covered LC oscillation? Tell me. LC oscillation circuit, have you studied or not? Yes. Did you cover LC oscillation circuit in your class? In EMI, it was covered. In your class, Sam, it was covered or not? LC circuit, which AC circuit? No, no, not AC. We are talking of LC oscillation circuit means this is we are talking about DC circuit only. This is DC circuit. Okay, briefly I will explain about this. Either this topic should be covered in EMI, so electromagnetic induction, or this should be covered in AC circuit. AC circuit I have not covered it here, but this topic I covered in school in EMI only. Okay, but we'll cover it now. It's not a big deal. It is not related with AC circuit. Okay. Okay, so how this type of charge appears, oscillating charges comes. So that you can see this circuit. It's not a big deal. Suppose if I say, for example, there is a capacitor. Okay, capacitor is there, and I connect with a battery, some voltage V. LC. There is a inductor L. So one minute. First, we'll consider that this capacitor is fully charged. Okay, this capacitor is fully charged, and there is a switch here. Right now, the capacitor is fully charged. It has a charge of plus Q naught and it's a minus Q naught. This is a inductor, inductance L. This is a switch. Now, at time equal to 0, you switch on. Time 0, switch on. If you switch on at time 0, then what happens? Let us apply the Kirchhoff's law. So it has plus minus, so current it will start discharging, so it will start sending current like this way, right? So let us say that this is some current at any time. At any time its charge is plus q and it is minus q. Okay, at any instant is time. So this current is going now. Now let us apply Kirchhoff's law. So in this loop, suppose if we go in this way, from this to this, we can write minus L di by dt. And then we go here minus to plus. So first of all, tell me current is increasing or decreasing here. That we need to think about it. Because should we write minus L di by dt or plus? Because this charge is decreasing, right? This charge is decreasing, so current will be decreasing. Current will be decreasing means by dt will itself will be negative. So let us write one extra factor here minus. Okay, minus of minus L di by dt will write, and then we go from here to here minus to plus plus. That is charge by capacitance. This is equal to 0. So from here what do you get? Here you get as L di by dt plus Q by C is equal to 0. Let us one more time you differentiate it. When you differentiate one more time, differentiating with respect to time, differentiating with respect to time. See, if current increases, so you can simply write minus L di by dt. But because current is decreasing, so di by dt itself is going to be negative. So that is why we are putting one extra negative here. Okay, so there should not be any confusion in this. Differentiating with respect to time is we differentiate. So further differentiation of di by dt will become double differentiation, and charge differentiation dq by dt will be there. Capacitance is outside. So from here we got L double differentiation d square I by dt square. That term will take that side minus 1 by c. dq by dt is current, so I am going to write this as current. Okay. So d square I by dt square becomes equal to minus 1 by LC into I. Now you need to pay attention to this equation. This equation represents as such a. You may say where it is representing as such a. So let me recall you what happens in SHM. In SHM equation, acceleration is equal to minus omega square x. I think all of you know that. Acceleration is equal to minus omega square x. All of you have studied that, yes? Simple harmonic motion, right? So if I write this acceleration is written as double differentiation of position. So d square x by dt square is equal to minus omega square x. Okay. So that's how you get this. Now you can compare double differentiation of position equal to minus omega square into position. Similarly here double differentiation of current is equal to minus, this can be taken as omega square into current. So if you compare these two equations, this is the oscillation of position and this is the oscillation of current. Okay, both you can compare. So if you compare means you can conclude that this is oscillation of position. This is oscillating position, and this is oscillating current. This is oscillating current. So we can directly write the equation, right? Because oscillating position, what is the equation of oscillating position? In SHM, you know x is equal to a sine omega t plus phi in general, right? We have studied SHM. This is SHM. Same manner, we can write this SHM also. This is current equation. So current is I equal to I naught sine omega t plus phi. This is also a SHM equation, but the quantity which is varying is current. Here the quantity which varies is position x. Clear? So we can write the current equation like this. Now you may say that current is changing. How is charge changing? Charge also change because current is what is I? I is dq by dt. We can substitute it, right? So I is nothing but dq by dt. dq by dt, that is what is this, right? I naught sine omega t plus 1. So if I integrate now, I will write dq is equal to I naught sine omega t plus 5 into dt, and then we'll perform integration both sides. When you perform integration both sides, this will become q, this will become I naught. Sine integration gives minus cos, so minus cos also comes omega t plus 5 divided by omega. Like this kind of equation you will be getting here. This is how charge is changing. Okay, you can clearly see this is like charge. Charge is also cos function, right? Cos function and sine functions are similar. If I write the magnitude of charge, so charge I can write as q equal to q naught. This become like magnitude of charge, become cos omega t. In terms of omega t, just right. Because see, when you take time equal to 0, time 0 means cos 0 is 1, charge is maximum. So initially charge was maximum only. You can use this equation. Okay. Also note that what is omega here? 1 by LC is omega square. Note that omega square is 1 by LC. And this omega comes as 1 by root LC. Where have you studied similar equation? Tell me. Omega is 1 by root LC. Where have you studied? No, last chapter. AC. Meaning AC. AC. Which topic here we studied? Omega is 1 by root LC. Resonance, correct. So this frequency is the frequency at which charge is oscillating or current is oscillating. Okay. So this is the frequency at which charge or current oscillate. Now current I can also calculate from here. I is equal to I naught. Differentiation I can do, and I can put a minus, so I will write the value of that. Okay. So current, if I differentiate this, what happen? Cos differentiation sign will come minus factor, but minus minus plus I will write, because current I is dq minus dq by dt. Here minus, if you want you can put it, not a problem. Then that minus will not come, right? If I put this minus here, then this minus will not come. That's why I am writing it plus. So equal to minus dq by dt. So that will become q naught into omega sine omega. This equation, you remember, this q naught into omega is like maximum current. It's like maximum current. I know. Sine omega. Okay. So this equation is giving us current. Here I naught maximum current is q naught into omega. Okay, so this idea of oscillating current or oscillating charges comes from which circuit? LC. This circuit is known as LC oscillation circuit. LC oscillation circuit. Okay. So in LC oscillation circuit also some questions can come, but not belong to this chapter. It belongs to EMI chapter only. Okay, electromagnetic induction chapter. Because EMI chapter, I think we have left few topics, if you remember, because it was late and you told to start next chapter. Remember that we have left in between EMI chapter. Otherwise, we could have covered that. It's okay. So this was not okay in oscillating. So done. I think this is what it is. The sources of electromagnetic wave, sources of so that means we can produce electromagnetic wave from this circuit. This circuit we can use LC oscillation circuit to produce electromagnetic waves. Now the question is, can light be produced from LC oscillation circuit? That is the question. Can light waves, because light is also electromagnetic wave, okay? Can light waves be produced from LC oscillation circuit? LC oscillation circuit. The answer is no. No, because the frequency of light wave is very high, very high. How much is that frequency? Visible light has a frequency of 10 to the power 14 hertz. Okay, visible light has frequency of 10 to the power 14 hertz. Very high frequency. We cannot produce. We can produce. We can produce low frequency electromagnetic waves in laboratory using LC oscillation circuit. LC oscillation circuit. What are low frequency? Low frequency electromagnetic wave means radio waves definitely can be produced. Radio waves. Okay, radio waves can be produced. Okay, so we can produce radio waves, because how will you define the frequency? That frequency already I told omega you can calculate, right? Omega is 1 by root LC. Let's take one example. L is capacitance is microfarad and L is, let us take millihenry. So suppose 1 millihenry I take 10 to the power minus 3 and 1 microfarad we take capacitance 10 to the power minus 6. So how much it will become? This will come 10 to the power minus 9 root under 10 to the power 9. You can take 10 to the power 8, 10 to the power 4 common, root 10, 10 to the power 4, right? Radian per second. And frequency is in hertz. So if I write omega is 2 pi into frequency, then root 10 into 10 to the power 4. Then this frequency will become root 10 by 2 pi into 10 to the power 4. Root under 10 is how much? Nearly it is pi only. So almost root 10 and pi can be cancelled. So 1 by 2 means 0.5. 0.5 into approximately 10 to the power 4. That means this is multiplied, so 5000 hertz only. 5000 hertz is very, very small, isn't it? So I have just taken one rough value. So we can produce 5000 hertz if you use a inductor of 1 Henry, 1 millihenry, and capacitance of 1 microfarad. If you use this, you can produce this electromagnetic waves of 5000 hertz or 5 megahertz you can say. Sorry, 5 kilohertz you can say. 5 kilohertz. Even megahertz frequency can be produced. Now you have seen in radio signal 96.7 megahertz. Metro cities, if you go Chennai or some other places, they have megahertz also, right? They have that. So, but we cannot produce that. 10 to the power 14 is very high. That we cannot produce. Okay, it's very difficult to produce that. You can take a very smaller values of. You can take a micro Henry also, or you can take a nano Henry, nano farad, nano you can take. Nano if you take -9, 18 factor will come. Maximum 18 factor means 9 factor will come. 10 power 9 will come. Nearly 1000 megahertz can come. 1000 megahertz can come, but 10 power 14 cannot come. Very high. So we cannot produce light waves in the using this, but definitely radio waves of higher frequency order we can also produce. Okay. That's what it is. Then we are going into the equations of electromagnetic waves, and we will write the formulas for the waves: energy, energy density, intensity, Poynting vector. After that, theories of electromagnetic spectrum will be there. The applications are there. With that, this chapter is one. Okay. So let us go into that. Okay, so characteristics of characteristics equation of electromagnetic waves. So electromagnetic wave, EMW, electromagnetic wave is made up of oscillating oscillating electric field and magnetic field. Oscillating electric field and magnetic field. Both electric field and magnetic field are perpendicular to each other. Perpendicular perpendicular to each other. The direction of propagation, the of wave propagation, direction of wave propagation is perpendicular to both electric field and magnetic field. So let us draw the diagram, a rough diagram. This direction is, let us consider this direction of wave propagation. This direction of wave propagation. Direction of wave propagation. Wave is propagating in x-axis. This is x-axis, and this is y-axis, and this is z-axis. So electric field is vibrating along this direction. Electric field will go up maximum, it will go down also minimum, right? Maximum minimum it will go. So electric field, if I draw electric field in this plane, like this will happen. Okay, magnetic field is oscillating in this direction along this maximum, along this minimum. Okay, so magnetic field is going, not going, it is oscillating in z direction. Okay, magnetic field is oscillating in z direction. So this is the maximum, that side is the minimum. So this graph, if I have to show, this plane will be like this. Okay. So the magnetic field is oscillating in this mesh It is going maximum, maximum, then decreasing, decreasing like this, becomes 0. Then it will go again maximum, but in negative direction it will go. Then it will come like this way. Then again it will go like that way. Similarly, the electric field is going up, right? Maximum, then go down, then again it goes up, then again goes down. Like that it will continue. Okay. So the electric field oscillation happens in this xy plane, and magnetic field is oscillating in uh, xz plane. Okay, xz plane is like a horizontal plane, and yz plane, xy plane is like a vertical plane. So electric field is oscillating in this vertical plane, and magnetic field is oscillating in this plane, which is the horizontal plane. Okay, and the wave is propagating, the direction of wave propagation is along x-axis. So now I will write the vector equation for this. So let us write the electric field equation. Electric field equation will be E naught sine omega t minus, it is going along x-axis, so omega t minus kx, or kx minus omega t also you can write. Some textbook they may write kx minus omega t. Okay, if you want to write kx minus omega t, kx minus omega t, and electric field is going along which direction? Y. So j cap we will put. Okay. Then magnetic field is along this direction. Magnetic field is also same way, V naught sine kx minus omega t. Which direction magnetic field? K cap. Okay, so this is the characteristics equation of electric field, magnetic field oscillation. Okay, and here you need to note that the direction of E cross V gives the direction of velocity. So let us say that this is the direction of velocity. Velocity V is wave velocity. Wave velocity. So you will see that this wave velocity V vector is parallel to E cross B vector. This is a very important thing to note, because if this is E and B is coming this way, so E cross B thumb will coming this way, right? This is E, this is B. E cross B will go this way, that is the positive x-axis. Sometimes they may change the direction, right? They may change the direction. So according to that, propagation direction will change. Remember, velocity vector is parallel to E cross B. Okay, all of you note down this equation. And a very important equation is that how is electric field and magnetic field value related? They are related. They are related together as E naught E by C at any instant E by C, that is equal to V. If you apply RMS or peak value, that also is, C means C is the speed of light. Otherwise, you may write it as V in general. If you want, you can put V. V means the speed of electromagnetic waves. Okay. So if I use this equation for amplitude also, we can write V naught is equal to V naught by V. Or I can use RMS also. VRMS is equal to ERMS by V. V is the speed of electromagnetic wave. But suppose it is in vacuum. Vacuum speed of light, you know, all electromagnetic wave travel with the same speed in vacuum. That also you can note. All electromagnetic waves travel with a speed c is equal to nearly 3 into 10 to the power 8 meter per second in vacuum. Okay. In vacuum, if you take, they are traveling with this speed. All the electromagnetic waves. Whichever electromagnetic waves are there, they travel with the same speed. Okay. And it is very, very important that the energy is stored in electric field and energy is also stored in magnetic field. We have studied that previously. That electric field stores energy and the magnetic field also stores energy. Okay. So if suppose electromagnetic waves are moving, so energy is stored both in electric field and magnetic field, and energy stored are equal. Okay. So let us do that, equate that. Using this concept, let us equate that. So energy stored in electric field is same as energy stored in magnetic field, and we have to take per unit volume, per unit volume. Here also per unit volume, per unit volume. So if you remember, energy stored in electric field per unit volume is half epsilon naught E square, and this is 1 by 2. Here 1 by 2 mu naught into B square. Do you remember that? This is what it is. This formula you have studied that. Half half will get cancelled. E square is equal to 1 by mu naught epsilon naught into P square. This I am taking in vacuum, okay? In vacuum. If you do not take in vacuum, then epsilon of that medium and mu of that medium you have to write. So if I take this E B by root under mu naught epsilon naught, right? This is what is C, because what is C here? We have seen that our speed is what? E by C is equal to B, right? So E is equal to 1 by sorry, C times of this, equal to C times of B. C is the speed of light in vacuum, the speed of electromagnetic wave in vacuum. So that's what we see here. C is equal to 1 by root under mu naught epsilon naught. Note down, this is the formula for speed. The speed is related with the constant mu naught epsilon naught. But suppose it is some medium is there, in a different medium, in a medium, that speed of light v will become 1 by root mu into epsilon. Then this mu can be written as mu r mu naught, and epsilon can be written as epsilon r epsilon naught. So 1 by root mu r epsilon r and 1 by mu naught epsilon naught will separate. So this v can be written as 1 by root under mu r epsilon r into C. This is a very important formula to note. Now this can be written as C divided by this factor we are calling as n. This n is called refractive index, that is going to be the next chapter in light. Here n is 1 by, not 1 by, sorry, n is root under mu r epsilon r. N is called refractive index of the medium. Refractive index of the medium, right? N is nothing but the refractive index of medium, which will be used in the refraction of light in the next chapter, ray optics, which is going to be a major chapter, whether it is JE or NEET or with board exam. Okay, refractive index. Done. So we have derived that formula also. Okay. This is what it is, 1 by root under mu naught epsilon. This is what, nearly 3 into 10 to the power 8 meter per second. Speed of light in Mach 1. Okay. So here now you need to note important thing that if I have to write the energy formula, energy, or let us write, yeah, you can write energy formula. What is energy in electric field? Is energy density per unit volume, or energy density means energy per unit volume only, multiply with volume. So energy density formula is what? Half epsilon naught E square into volume you will do, right? So you see, whenever you are doing volume, and what is electric field? Electric field is E naught sine omega t kx minus omega t, right? Remember that just now we have written kx minus omega t. This whole square you have to do into volume. So let us write this energy. Let's write divide by volume. Let us write energy density only. Energy density in electric field. That will become half epsilon naught E naught square sine square x minus omega. But now if I will take average value, because see, this is energy density in electric field, but I will take average value. Average energy density in electric field. Average of sine square function is half, that you already know. Sine square function is half. So half become 1 by 4, 1 by 4 epsilon naught E naught square. Okay. Similarly, we can write energy density in magnetic field. Energy density in magnetic field. 1 by 2 mu naught B square will give us B naught square sine square Px minus omega t. And when we take average value, average energy density, in magnetic field, again sine square function gives 1 half. That's why it will become 1 by 4 mu naught into B naught square. Okay. But now suppose I want total energy density average. Total average energy density. Let us add total. And you should know that this, note here that 1 by 4 epsilon naught E naught square is same as 1 by 4 mu naught into B naught square. So we already know that they are equal because energy is equally distributed in electric field, magnetic field. So now I will write the average energy density, in electromagnetic wave. Average means we are adding this also plus this also. So here you are adding 1 by 4 epsilon naught E naught square plus 1 by 4 mu naught B naught square. But they are equal, so you can write in terms of either electric field or magnetic field. So they are equal, so 2 times of this or 2 times of this you can write. So it will come half epsilon naught E naught square, or it can be written as 1 by 2 mu naught into E naught square, right? This is the average energy density. Okay. And what is meant by intensity? Also note what is meant by intensity. I think you have idea of intensity. Note that intensity is energy energy per unit area per unit time. Okay, intensity is energy by area by time. Okay, energy by area by time. Now let us convert this as energy by area into time into uh, distance divided by distance. Distance we can multiply in numerator denominator. Right? Distance I can multiply. Then I will rearrange this as energy by area into distance. Area into distance I will take, and distance by time I will club this side. Distance by time. Okay. So energy, area, distance I club together, distance by time I club together. So note here that energy by area into distance is volume, that is what is energy density. So intensity can be written as energy density, energy density into distance by time is speed of wave. So intensity can be written as energy density. Energy density we have already seen that we can use. If I write total intensity of electromagnetic wave, average intensity if I write, so 1 by 2 I will take, so 1 by 2 epsilon naught E naught square into speed of wave v. This I can also write as 1 by 2 mu naught b naught square into v. Okay. Note that we are writing average intensity in electromagnetic waves. Okay. So that's the formula for average intensity in electromagnetic wave. Now the same formula for average intensity can also be written as Pointing vector. Pointing vector can be written as 1 by 2 epsilon naught E cross B. Check out this whether this is correct or not. Because if I write E factor E by C, E by C is equal to B, right? Check out whether this is coming or not. E by C is equal to B. So E becomes C times of B, correct? So what can we check that? Check that 1 by 2 epsilon naught. E vector I am writing as C times of B into B. So 1 by 2 epsilon naught B square into C it has come. But let us bring in terms of mu naught. Or if I want B, I can substitute in terms of that. B also we can substitute. Because it should come like this form 1 by epsilon naught into this. Can we bring that? What is C? C is under root epsilon naught mu naught. C square becomes 1 by mu naught epsilon naught. Right. So epsilon naught C square becomes 1 by mu naught. So I think we need to multiply one C in numerator and one C in denominator. Multiply this. Multiply one C in numerator and denominator. So we will get 1 by 2 epsilon naught C square into B square by C. This become 1 by 2. This become mu naught will come in denominator. B square by C is coming in denominator. It is in denominator or numerator it is. Pointing vector, let me check the formula for pointing vector. It is not given in NCERT, but in some textbook it will be there. No, it is given 1 by mu naught. Correct this one. Average, if I take 2 factor, I will take, okay, if I take average. 2 factor come when you take average energy. Okay, so take it as this formula 1 by mu naught, 1 by mu naught, E cross B. Okay, this pointing vector is represented as S vector. S vector is energy going in a particular direction. Okay, now you check this whether are we getting the same thing or not. Check that. Do you get this? Try to check the magnitude of this 1 by mu naught E into B. See, angle between electric field and magnetic field is 90 degrees, so sin 90 degree will become 1. Okay, so 1 by mu naught E into B. E is what? E by C ratio is equal to B. So E I will write as C times B into B. So B square by mu naught into C. But if I take average pointing vector, average pointing vector, average pointing vector can be written as 1 by 2 mu naught E cross B, right? Because whenever we take average, that will come, of course, E naught amplitude will come whenever we take average. Now you see here average, if I take half, I will put it. So its magnitude will come as 1 by 2 mu naught E naught square into C. Check out this. Average, if I take like this, or if I don't take average, then this is the pointing vector problem. But pointing vector is the same thing which we are getting here, average intensity. You can clearly see here half mu naught V naught square into V. V is the speed of electromagnetic waves. Clear? So what is pointing vector gives? Pointing vector gives that energy density into the speed, how energy is propagating in space. So in this direction, energy is propagating in this space. So that is what it is a pointing vector. The name pointing is based on the scientists who have given it. Okay. So energy in the electromagnetic wave is propagating in this direction. How much energy propagating per unit volume? Per unit volume. Suppose I take this 1 centimeter cube. In 1 centimeter cube, how much energy is going in this direction? That is the meaning of that pointing vector. Yes, are you clear about it? Anyone any doubt in this? So I think let us wind up till here. Now the next topic which is remaining is theory only. Theory means what? What is the use? What are the electromagnetic wave? Different type of electromagnetic wave and applications. Tomorrow that will finish. Okay, tomorrow. So that is means like what are X-rays? X-rays are used in medicine. What is like different wave lasers, where are the applications of lasers, then different like gamma rays, radio waves are used in communications. But in NEET or in JEE they are asking definitely questions on this year also. NEET, you see some questions are asked. Where is microwave used in cooking, right? All these applications you have to remember, plus you need to remember the frequencies or the wavelengths. They are asking questions of that. Radio waves, how much wavelength it is, some kilometer ranges it can go. So in NCERT there is a table given, that table we have to mark up. Okay, and which waves are produced by which, means in laboratories, what methods they are using, those things also we have to mug up. Before the re-NEET happened, when the NEET was there, 3rd May, that time also they asked some question from exactly from NCERT table, they asked that question in NEET. And in re-NEET also they have asked the similar applications like microwaves used where, X-rays used where, like that. You can watch that video where I have made, right, both of that videos. That is there. So after means next class we'll wind up this. Then we can go for question. That means two more classes will be required. One class will wind up that. We'll start problems, and one more class on the problems. We'll finish that. Then light waves will go of ray optics. Okay, reflection, refraction, all the things will start. Fine, right? So thank you all for your attention, and we will see in the next class about. Hmm. Hmm?